Number 2, the Cauchy transform. Which we had denoted as C of zeta, the Cauchy transform of the characteristic function of omega extends as a rational function. So by this I mean there is a rational function R of zeta such that the Cauchy transform equals R on the complement of omega, C minus omega. There was a little digression that we had last time. The digression was about the definition of the Cauchy transform. So let me just write this here. This is the integral of 1 over z minus zeta dA z. And you integrate here. So this is the convolution of the characteristic function with 1 over z. So we had identified a number of properties. So this is continuous everywhere. And since we are dealing, so I also wrote down an estimate. So C of zeta is big O half near infinity. But as Kaushik pointed out after yesterday's lecture, you can do much better if your domain is bounded. So since this is bounded, C of zeta is in fact big O of 1 over zeta. So the Cauchy transform vanishes at infinity. But in general, this is the best that we can expect. The d bar derivative of the Cauchy transform is minus pi times the characteristic function. And so if you happen to be outside the domain, then the zeta bar derivative is 0. So therefore the Cauchy transform is holomorphic outside. Holomorphic outside. And in this theorem here, if C were to be equal to a rational function outside, this forces all the poles of R to be inside the domain, because C is holomorphic outside here. Yeah? And the other thing that was mentioned was that the Cauchy transform can be written as minus pi times zeta bar plus a holomorphic function on omega. Here G is continuous on omega, holomorphic on omega and continuous on the closure. So the little digression from last time, coming back to this theorem. The last part of the theorem says that there is a meromorphic function S of zeta on omega, such that S extends continuously to the boundary and it equals zeta bar there. So this was the main theorem. So statements 1 and 2 were shown to be equivalent, and I believe we also showed that 2 implies 3. In other words, if you have this equality, that means you have a rational function. There was a way to create this meromorphic function. And it's basically R minus G. That's the definition of the Schwartz function here. All right. Now to complete the proof of the other equivalence, namely 3 implies 2, there's another theorem that we will need. I think I wrote this down yesterday. I'll just repeat myself. Omega is bounded, and suppose f and g are meromorphic functions on omega, and f and g extend continuously to the boundary. And take real values there. F and G are both real valued on the boundary. Then there is a polynomial in the indeterminates x and y with real coefficients such that, in this polynomial such that P of f of z, g of z is identically equal to 0 on the domain omega. And furthermore, we can choose this polynomial P to be irreducible over C. Okay, so this is saying that whenever you have a pair of such functions that are real value, then they must be algebraically dependent. See, what is really happening here is, suppose your domain omega were to have nice boundaries, say for example, bounded domain, then you could take another copy of the same domain and glue the respective boundaries. In other words, create the Schottky double. You get a compact Riemann surface in that case. So your Riemann surface has two halves, the upper half and the lower half here. You have your functions f and g that are defined on the lower half. Yeah? And in case they happen to be real valued, you can actually reflect them to get holomorphic functions on the upper part here. So when I glue these two things together, I get a pair of meromorphic functions on a compact Riemann surface. In that case, it's known that there must be an algebraic relation between them. So that's the moral of this theorem, but we are not making any assumption on the boundary of omega and so on. Just arbitrary. And this theorem is also true if omega happens to be unbounded. There are some generalities that you can allow, but this is enough for our purposes. That's what's behind this theorem. Okay, so what I want to do is to I'll give you the original proof of this theorem. I think I really like this very classical pole counting argument, which it's a very useful thing to have in our toolkit. Maybe tomorrow and in the last lecture also, I'll indicate more contemporary proofs of this. So, but I think it's good to understand the original argument. This is in the same paper of Aharanor and Shapiro. So what do you do? Let's look at the following set. So A is a set of all poles f and g. So don't count multiplicities, but just put them together. Let m be the number of poles of f and g counting multiplicity. So what we do is to consider the following collection of functions. So for each n, consider f to the j times g to the k. Look at powers where j and k are both non-negative and their sum is at most n. You look at monomials of this kind. So this should remind you of x to the j, y to the k. So I'm looking at all these monomials such that the degree is at most n. So there are going to be exactly n into n plus 3 divided by 2 such functions in this collection here. So many monomials. On the other hand, if I look at any function of this form, f to the j, g to the k, its poles are all going to be in this big set capital A. I don't create new poles just by multiplying two functions, right? And and the total multiplicity of the poles that are created this way does not exceed m, which is the largest number counting multiplicity, times n here. Because the highest degree is n, and the maximum contribution of f and g both together is m. So, so all poles of f to the j, g to the k lie in A, and their multiplicity does not exceed m times n. Now, what you do is, since each of these are meromorphic functions, you can expand them as a Laurent series around each of their poles. So I have finitely many elements in the set A. I look at the singular parts of each of these functions. Yeah? So they're going to be the following form. So consider, so let V be the vector space of the principal parts of f to the j, g to the k. Okay. And because the total multiplicity does not exceed mn, the real dimension of this vector space over R is at most 2 times mm. Yeah, is clear? So I look at the singular parts around all the points in capital A. Forget the holomorphic part. The singular parts are generated by monomials of the form 1 over z minus some q to some power. I look at the span of all of these. Total dimension over R is at most 2 mm. But now, if I choose n large enough so that n into n plus 3 by 2 is bigger than 2 mn, if I do that, then what will happen? Choose n so that so I'm taking more number of elements than there are in the basis. So there has to be a combination, a linear combination, which adds up to 0. So I look at that linear combination, and that is my relation that I'm looking for. So there is a relation, polynomial relation, say q xy such that q f of z g of z. This is in fact a holomorphic function. So we've eliminated all the poles by taking a polynomial of large enough degree. So this is the pole elimination, pole counting technique here. Okay. And also note that just by construction, q of xy is a polynomial with real coefficients. I'm looking at real degrees here. Okay. Well, we are almost done. We're almost done. Because yeah, so q of f z gz is a holomorphic function. By construction, q has real coefficients. And what happens on the boundary? If you go to the boundary, both f and g are real valued there. So this is the holomorphic function whose imaginary part is 0 on the boundary. Hence, q of f of z, g of z, is 0 on the boundary. Okay, so we have some relation. And now the point is to show that you can choose such a relation to be irreducible over C. Okay, so what you could do is to look at all possible q's that arise by this procedure. And I look at that q which has the smallest degree. So let P be that polynomial relation with smallest degree, say D. The claim is that this is irreducible over C. So if this were to be reducible, then I could write P as a product of, say, P1 and P2 over C. One is tempted to think that because of the minimality of degree we are done. There's just one sticky point here. When I express P as a product of P1 and P2, I'm assuming that this is reducible over C. I do not know if P1 and P2 have real coefficients. So I need to ensure that that point is taken care of. So suppose P can be factorized as P1 times P2, where these are in C of xy. And the degrees of each of these PIs is less than D, strictly less than D. Okay, so now let's look at P of f comma g, which is by definition P1 of fg times P2 of fg. When I plug in these two meromorphic functions, PIs are polynomials, so on the right hand side I get a product of two meromorphic functions. P is the relation with least degree, so this is 0. So I have a product of two meromorphic functions, which is 0. Therefore, at least one of them must be identically 0. Okay. So what we'll do is we'll write down P1 as the P1 of xy as P3 of xy plus I times P4 of xy. So just split this into the real and imaginary parts. And what happens if you plug in f and g? on the right hand side. Well, this is equal to P1 of f comma g, which is 0. So this is 0 even on the boundary of the domain omega, because f and g have no poles there. But the other interesting thing is, you see, I claim that since f and g take real values on the boundary, this is real and this is real. There is no further decomposition into real and imaginary parts here. These are the real and the imaginary parts of this expression here, because f and g are real on the boundary. Okay? So since f comma g on the boundary are real, I can conclude that P3 of f comma g is identically 0, again by the maximum principle and so on, and P4 of f comma g is 0 on the boundary, on the entire domain. Okay. And this is the contradiction that we are looking for. P3 and P4 are polynomials in the ring R of x comma y. Each of them has degrees strictly less than d, and here is a relation of strictly smaller degree than what we started out with. There's just this technical point. So that's the contradiction. Any two meromorphic functions that are real valued on the boundary are algebraically related. Okay. So now let's use this theorem to complete the proof of the basic theorem here. Okay, so what do I want to show? I want to show that 3 implies 2, and then we'll be done. All right, so what do I want to show? I want to show that the Cauchy transform agrees with a rational function outside. And what am I given? I am given that there is a meromorphic function S which equals zeta bar on the boundary. So let's create a new function. So define f of z to be the Cauchy transform on the complement of the domain, and inside we define it to be g of z minus pi times s of z. So outside the domain, your function capital F is holomorphic just because of the properties of the Cauchy transform. Yeah. So this is holomorphic outside, and in the domain omega, I have a bunch of poles coming from S that's given to me by assumption, and G is a holomorphic function there. So capital F has finitely many poles inside, and what happens on the boundary? Well, these two things agree, because S is equal to Z bar there, and C agrees with minus pi times Z bar plus this G, just by the properties of the Cauchy transform. Yeah? So I have my domain, I have defined a new function equal to the Cauchy transform outside, something else inside. What exactly? So I need to patch these two things up. When can I do the patching? I can do the patching if it's nice enough. But I know that the boundary is, well, I should have written the corollary. So I'll take a digression just for a minute before I can complete. So here's a corollary to this statement, the algebraic relation here, corollary. It's very important. I missed this. So every bounded quadrature domain has the following property. There is a polynomial p of xy irreducible over R. Such that the boundary of omega is in fact contained in p of xy equal to 0. So x comma y in R2, such that this is true. Okay, so how do you quickly prove this? Well, so just to make sure that there is no circularity in the arguments, I wanted to show that 3 implies 2. Okay, so I'm given the existence of this Schwartz function S, which equals zeta bar on the boundary. So let's create 2 new functions. So look at, define f of z to be 1/2 of f of z plus z, and g of z to be 1/2I z minus s of z. S is meromorphic, and therefore f is also meromorphic. Both are meromorphic on omega. And what happens on the boundary? S is equal to z bar. So this is z plus z bar divided by 2. So this is x, which is of course real valued, and g is y, which is also real valued. So I have 2 meromorphic functions which take real values on the boundary, and therefore by the theorem that I just erased, there is a polynomial p of xy which is equal to 0 on the boundary. So should be a little careful here. So what does the theorem say? The theorem says that f and g are algebraically related by this polynomial here. But on the boundary, f and g are exactly the coordinate functions x and y. So this reduces to, so just write this down. So every point on the boundary satisfies this relation, because x comma y is exactly equal to f comma g, and p is a relationship between f and g by that theorem. Okay, so that's the nice part, the algebraicity of the boundary of the quadrature domain. And then now we can patch this two theorems, two functions up, because outside you have c of z, and inside you have g of z minus pi s of z. And on the boundary they agree. The boundary is very nice. So I get a holomorphic function which has only finitely many poles here inside. This must be a rational function. And what happens at infinity? At infinity, C is very well behaved. There's no problem with this. So capital F is a rational function. So, conclusion, capital F is meromorphic on P1. A rational function. So C is equal to R. There is, hence, 3 implies 2. That's the main theorem. Okay. So this is a very nice conclusion, namely the existence of this irreducible polynomial, real coefficients. And this automatically now gives us several examples of domains that are not quadrature domains. You look at a triangle, for example, it's bounded by 3 linear lines. This cannot be expressed as the zero set of an irreducible polynomial. So 3 distinct branches. So a triangular region is not a quadrature domain. Non-examples. A triangle is not a quadrature domain. And secondly, you could also look at an honest annulus, inner radius R1, outer radius R2. So again, if you try to write down a defining function for this, you're going to have one component of the form mod Z1 minus R1, and then other component will have Z2 minus R2. So it's always going to split up. It's not going to be reducible. So this is not a quadrature domain. An honest annulus is not. But as we sort of briefly mentioned in the first lecture, quadrature domains are going to be dense in the class of smoothly bounded domains. If you just perturb this a little bit, there are lots and lots of quadrature domains nearby. And that's surprising. That means there are irreducible polynomials whose zero sets contain these 2 distinct components. Okay. So that's one basic foundational theorem in this subject. Yes. So we'll discuss this in tomorrow's lecture. We'll try to identify P as best as possible. So we can say plenty of things about P. In fact, we can identify what the leading term should be. It should be of the form x squared plus y squared to some even power. And if we grant this, even an ellipse will not be a quadrature domain, because A is not equal to B, the eccentricity. That's for tomorrow. Yeah.
Cauchy transform of the indicated function in omega is the given raised function. Or this, my question is this raised function that we have, is it going to have some more rigidity, or we can say starting with a raised function, we can construct quadrature differential form.
Okay, so I'll try to answer your question by proving one more theorem here. How do you use rational functions to create many examples of quadrature domains? But before I do, here is a very, very nice theorem. An old theorem due to Epstein and Schiffer. The theorem states the following. Suppose omega is a bounded domain. And assume without loss of generality that the origin belongs to omega. And suppose you know that there is a quadrature identity of this kind. So if I take any integrable holomorphic function on omega, this is a constant a times f of 0. Some a. Non-zero. This is true for in L1 O. The theorem says that then omega is in fact the disk with center 0 and of a certain radius which is related to this constant here. The nice thing is, it's not saying that omega is biholomorphic to a disk, but omega is the disk. So if we sort of recall some of the things that went behind in our discussion yesterday, the quadrature identity that you get, so that comes once you specify a bunch of nodes, those QIs. And the proof of this theorem reveals that the Schwartz function S has its poles precisely at the nodes. This is something we discussed in that proposition from last time also. If you have a bounded simply connected domain with nice boundary, then by using Green's theorem, we were able to push the integration from the boundary inside to the poles. And S was assumed to have poles exactly there. So, what is our given data? Our given data is the existence of a quadrature identity where you have point evaluation at one point, the origin here. No derivatives involved. Yeah? So, the corresponding Schwartz function for this quadrature domain is going to have a simple pole at 0, nothing else. As a simple pole at 0. And on the boundary, it's equal to Z bar. So let's look at Z times S of Z. S times Z of S is now a holomorphic function. You've eliminated the pole now. This is a holomorphic function on your domain. And on the boundary, S times Z is equal to Z bar, which is mod Z squared, which is real. And therefore, by the identity theorem, S times Z, S of Z is real, constant real, it's constant, see, R. But then the boundary, we were able to control the boundary, remember, by defining these two functions, F and G. So take a look. So consider those two functions, square them and add. If you square them and add, you will get exactly 2 times ZS. So this is real constant 2C. And what were F and G on the boundary of your domain? F was equal to X, G was equal to Y. Therefore, the boundary is described by squared plus Y squared equals. It's in fact a subset, because that conclusion says that the boundary is contained in the 0 set of this irreducible polynomial. Your polynomial here in this case is just X squared plus Y squared equals positive constant here. But then I'm assuming that the domain is bounded, so I cannot miss any point on the boundary. So it is the disk. That's the Epstein-Schiffer theorem. Very now, this has been sort of very thoroughly understood. You can drop these hypotheses of boundedness and so on. This is applicable to a very large class. So there's an analog of this theorem in higher dimensions Rn also, where the test class that you consider is the class of all harmonic functions. If you have a one-point quadrature identity for the class of integrable harmonic functions, then you are the ball, nothing else. Okay. This theorem remains. Okay, Vikram, I'll try to answer your question now. How do I create examples of these using rational functions? Again, in the same paper. So this theorem actually gives you a characterization of all simply connected quadrature domains. And the proof will tell you how to create as many examples as you want on a given day. There's no dearth of them. So omega bounded and simply connected. Then omega is a quadrature domain if and only if the following property holds. And what is the property? That phi be the Riemann map from the unit disk into your domain, Riemann map. Let this be the Riemann map. I should state it properly. If and only if the Riemann map phi is a rational function So this gives you a hold on the domain being a quadrature domain in terms of the Riemann map. So it's saying that Riemann map must be a rational function. It says something more. So furthermore, well, if you happen to be a quadrature domain, then you would like to know what the nodes are, what the quadrature identity is, and so on. Also, let also, okay, again, let me state this carefully. Also, if TIs are the poles of phi, in this case, then let's keep this picture in mind. So all the TIs are outside, This is my Riemann map phi to the domain omega. Well, each of these points can be reflected inside, right? So this is 1 over pi bar. So I can push forward each of these points, phi acting on the inversions of these points. Then omega as a quadrature domain has nodes at. You can guess what the answer is. So I reflect all these poles inside, I get finitely many things. I push them forward by phi, I get a bunch of points in omega. What are these points? The points are phi of 1 over pi bar. So these are exactly the nodes, the quadrature domain. If you actually want to know what the quadrature identity is, then the procedure is exactly what we did in the proposition from last time. So I now know what the poles are. I want to integrate a function on the boundary. I'm also simply connected, so I push the integral inside and integrate along each of these, which means I compute the singular part around each of these points, and that gives me the quadrature identity. And also know what the quadrature identity is. Quadrature identity. Okay, so as I said, there are two parts. Every bounded simply connected domain is a quadrature domain if and only if its Riemann map is a rational function. It extends everywhere. And of course, this statement implies that all the poles of the rational function have to be outside, because in the interior phi is holomorphic. In this case, if pi's are the poles, then you can say something more about the quadrature identity. Reflect, push it forward. And these are the nodes. Now, this gives us a way to actually construct many examples of simply connected quadrature domains. All you do is you take any old rational function, identify all the finitely many poles, throw them away. In the complement, choose a small enough disk on which your rational function is injective, push that forward by means of the map phi, the resulting domain is a quadrature domain. And this theorem also identifies what the nodes are. You can create quadrature domains in which the identity is as complex as you want. That's the idea. Give you a quick proof and then give you an example, a bunch of examples. Let's just do one half of this theorem. So suppose that omega is a quadrature domain, simply connected, bounded. So here's our picture. Here's my disk. Here's the Riemann map. This is omega, and I have the Schwarz function, S of z. This takes values in P1s, the holomorphic map. We also know that the boundary is real algebraic theorem. And therefore, by the classical Cartesian theorem, this Riemann map actually extends continuously to the closure here. It takes the boundary to the boundary. So phi extends continuously to S1. And S of phi of t So what happens if t goes to S1? So phi of t is going to land on the boundary where S of z is equal to z bar. So S of phi of t is phi of t bar when mod t is 1. So what's our goal? Our goal is to show that this map phi is in fact a rational function. Okay, so let's define two inversions. So this is phi of 1 over t bar bar mod t bigger than 1. So this you will recognize is the classical recipe to extend anything on the unit disk which is real valued at the boundary. So this is a holomorphic function and psi of t is equal to so if you are on S1 then 1 over t bar is equal to t. So this is phi of t bar and phi of t bar is the value mod t equal to 1. Okay. So then look at this function r of zeta which is equal to psi of t outside and it's equal to s of phi of t inside. Yeah, so we've created two new functions. One is just reflect this phi, this is psi, and on inside I'm just composing these two functions here, s composed phi. So the patching again happens because the boundary is real algebraic and they agree there. So this is the holomorphic function and it has poles where are the poles of this guy? The image of let's see. Yeah, okay. See, where are the poles? The poles are only going to come from the Schwarz function. This guy is holomorphic outside here. S has poles only inside, but S is defined on omega. I'm composing this with phi. So R is going to have poles only inside the unit disk. And where are the poles going to come from? So I pull back the poles of S. That's what this is. So R has poles inside the disk. Only inside. Huh? S is equal to Z bar, so there's no pole, it's all only inside. Yeah? And everywhere this is holomorphic. So this is your rational function. And we're all done because now what does this tell you? Look at psi. Psi is two inversions of phi. So two inversions of phi give you R outside the unit disk. And therefore, phi of t can be written as, so I'll just complete the proof here. So the Riemann map can be written as R of 1 over zeta bar bar. R is a rational function. You have two inversions, so this is holomorphic, and that's exactly equal to the Riemann map. Your Riemann map is a rational function. I'll just take 2 more minutes and give you some examples. And in creating these examples, we'll use this theorem in exactly the same manner as I told you. Start with the rational function, throw away the poles, and look at a disk on which phi is injective. Push the disk forward, the image is your quadrature domain. Some example. So look at phi of z, which is z plus c times z squared, where modulus c is less than or equal to half. So this is a polynomial, infinity is a pole, order 2. And because of this condition, phi restricted to the unit disk is injective. And therefore, by this theorem, the image of this is a quadrature domain. And what can you say about the identity? Say something? Well, again, this theorem tells you plenty of things. So there's a double pole at infinity. And if I reflect infinity in the unit disk, I get 0. And because this is a double pole, if you do this proof a little more carefully, the order of the quadrature identity will be 1 less than the order of the pole there. So the quadrature identity takes this form. So I integrate any f on this omega. This is going to be some a times evaluation at the inversion plus b times f prime 0. So 1 less than the order. You can find out what a and b are. So the thing is, Vikram, you work on a sufficiently small disk which does not contain any of the poles, and you take its image with the understanding that phi is injected there. You play this game once again. Take phi of z to be say z times 1 minus p squared z squared or 1 minus q squared z squared. P naught equal to plus minus q, and small. Both are small. So this is like a perturbation of the identity in some sense. So phi of the disk again is a quadrature domain. And the identity in this case takes this form. So what are the poles? The poles are at the points plus minus 1 over q. And there's one at infinity. So I invert all these 3 points. And all of these are simple poles. So in your quadrature identity, you will not have any derivatives. In fact, you will get a linear combination of evaluations at these nodes. So this is the integral of a times f of something plus b of something else. There's something else I can compute. Infinity gets inverted to 0. Okay, so these 2 stars are in fact plus minus q bar, inversion of this. That's your quadrature identity. I have one more example, but I think we'll work that out in a little more detail. I think I'll stop here for the day.